This is Jack Jackson again, and we're going to look at Simpsons Rule today. This is going to be a method, actually a very powerful method for approximating a definite integral. So let's just review a couple of things real fast from this set of notes. First of all, the basic thing that we're trying to do is we're trying to approximate the area under a curve, which say might be, for a function like this one, might be an area like this. For now we're assuming the function has a positive value here, but we can come up with whether or not it's positive value. We want to come up with this areas here. So we found that we could approximate that on each piece by a little horizontal line segment with the height at the right end of the interval, making little rectangular areas. So we're breaking that up into sub-intervals. On each interval, find the area of a rectangle. Okay, with that rectangle's height is at the right end of the interval, we call this sum a right Riemann sum. On the other hand, if we make the rectangles have heights at the left end, that's a left Riemann sum. We found that we could improve that because if the function were constant on the interval, both the right and left Riemann sums would be the same as each other and the function, and the area under the function, and it would be the same as the function being constant on that interval. But if the function's increasing, the right and left Riemann sums will both be off a bit, with the right Riemann sum being too large and the left too small when the function's increasing, but exactly reverse when it's decreasing. The fact that these are backwards means that we could average them and get a better estimate. So there's the right and left Riemann sums are these, say on just one interval would be a rectangle here and here. If we average them, we get a rectangle here that's the average height. Notice the height is exactly halfway in between. We saw that we could also see, because of this picture here, we saw that we could represent that as one rectangle or as one trapezoid in terms of the area. So these areas are the same. So the trapezoid rule, which is the average of the left and right Riemann sums, is the same as approximating the function with a linear function, which is a secant line between the endpoints on that particular interval. In other words, the area of that trapezoid, hence the name Trapezoid Rule. We also saw another way we could estimate something is through the Midpoint Rule. And the Midpoint Rule is, it's a Riemann sum as well, but instead of doing the height of the rectangle at the right or the left end, we find the midpoint horizontally here. So halfway between both ends of this interval horizontally, find that x value, go up, and where that meets the curve, that's going to be your y value, or for the height of your curve there, height of your rectangle. Okay, and then find the area of that. So that's the area of rectangles added up, and that gives you a midpoint rule. We also saw in our last video that we get an area of a rectangle like that, but because of the way this picture is drawn here, it's the same as taking a tangent line across here and finding the area of that trapezoid. So like the trapezoid rule, we can estimate the area or visualize the area as an area of a rectangle, but also as an area of a right trapezoid. This time the top of the trapezoid, instead of going from this point to this point on the curve through a secant line, it takes the point in the middle horizontally and finds a tangent line there and approximates the top with that tangent line. So that forms the top of our trapezoid. So this green area and this area over here are the same areas. So there's an example of the trapezoid rule. Now let's take a look at another function, and this has both the midpoint and trapezoid rule trapezoids illustrated. So let's look carefully. Let's look at these first two pieces. Actually, it's four pieces here. But let's look at the first two pieces. And in these two pieces, the function is concave down. Notice that the trapezoid from the trapezoid rule uses the top of the trapezoid to be the secant line segment. So it goes from this point right here on the curve to this point for the first trapezoid. The dividing line between the trapezoids is this vertical line right here at looks like -1 for x. And so it's the area of this more darker shaded part here. And then we have a similar decreasing but concave down situation here, again this way. So notice when the curve is concave down, those secant line segments will be below the curve, and the trapezoid rule will be an underestimate of the actual area. Whereas if we look at the midpoint rule, still concave down, we're going here in the middle, coming up, finding the tangent line there, and that makes the top of a trapezoid here. So this is a lighter shaded. It goes all the way down to the axis down here. And so this total area there is our part that goes into the midpoint rule estimate. Notice that it's when the function is concave down, whether it's increasing or decreasing, the tangent line is above the curve, and the function is the area under the function is actually less than the trapezoid area there. So the midpoint rule will be an overestimate whenever the function is concave down, and the trapezoid rule will be an underestimate. Now what if the function is concave up? Look at these two pieces over here. So over here, now if the function is concave up, the gray areas, which go all the way down to the axis, are the trapezoid rule trapezoids. Okay, and so notice that when the function is concave up, the secant line, which is the top of the trapezoid for the trapezoid rule, is actually above the curve, whether the function is decreasing or increasing, like over here. And we see that whether if it's concave up, the secant line is above the curve, and the trapezoid rule will be an overestimate. And in this case, the tangent line is below the curve when the curve is concave up, and so the trapezoids that you see here are actually too small. Actually, this last one looks like it might even be actually a triangle rather than a trapezoid. But in any event, the trapezoidal rule gives you the bigger trapezoids here, and the midpoint rule gives you the smaller trapezoids when it's concave up. So bottom line is, we have the trapezoid rule is too large, or it's larger than the actual integral when the function is concave up, and the midpoint rule is too small, and it's exactly reversed when the function is concave down. Once again, good news. What's the good news? The good news is that these are opposites, so that tells us that we should be able to get a better estimate. How can we do that? Well, we average them. Now, we want to be a little bit more careful here this time. There's no reason to believe that the left or right estimate is either one's better than the other one necessarily, or in general. So we just did a straight average of the two to find the trapezoid rule estimate. And we saw that it has a nice visualization as the area of a bunch of trapezoids with secant line segments to the curve for the tops of the trapezoids. But if you look at this particular one of these actually is better than the other one. Let's just look at this first trapezoid right here. Do you see that the midpoint rule trapezoid is above the actual curve? By how much? Well, this little area right in here, and this little area right in here. And then let me see if I can actually do a little shading. So this area right here, okay, plus this area right here is how much the trapezoid rule is, that's to how much it's over. Okay, similarly, say this area right in here, whoops, I want a different color. Let's try that again. Okay, so that's how much the midpoint rule is over. And if I go, come on, right in here, this much is how much that the other one, the trapezoid rule, is under. So look at those two areas. They're clearly not really that close to the same value. In fact, if you look at it, the green area is about twice what the blue area is. Actually, for this function, the green one is exactly twice what the blue one is. So, we're going to weight the better one twice as much as the other one. Well, the better one was the midpoint rule, right? The blue area is the area on the midpoint on that one rectangle anyway. One trapezoid, and by the way, this is the dividing line. So we're looking at this part down here they have in common, and then we're looking at comparing the top here for the midpoint for the trapezoid rule versus up there for the midpoint. Okay. Alright, so with that, looking at it, we see that the midpoint is going to be better. So when we make our approximation this time, that's going to be better. When we do our average, it's going to be a weighted average, and we're going to weight the midpoint twice as much as trapezoid. So we're going to do midpoint plus trapezoid divided by 3 this time. So in other words, 2 midpoints was 1 trapezoid divided by 3. And this is going to be called Simpsons Rule. Now, my way of thinking is that we take that this is one interval right here. And notice we're taking information on the curve right here in the middle of the interval, at this end, and at this end. So we're taking that as one interval with information taken at both ends in the middle of the interval. So I would think of this as being broken up into 4 intervals here. On each one we're taking information from the middle and both ends to figure this out. Now, most books, when you see talking about Simpsons Rule, they'll actually divide this up like this and say that's 8 intervals instead of just 4. I prefer to call it 4 intervals. Okay, so when I refer to it, I'll call it 4 intervals. Just be aware that in many books, when they talk about Simpsons Rule, actually on most every book, they're going to call it twice what I call that. And they'll insist that the number is even. The number of intervals is even because they're just doubling what I'm calling one interval. So, using our estimates from above, we knew the midpoint for this integral, so we're back to x to the 5th dx, integrating from 0 to 2. So n equals 4 rectangles. I'm going to call that S4. Most books would call that S8. It would be 2 times the midpoint plus the trapezoid divided by 3, and this gives you the result that we want, which is about 10.67, so forth. In this particular case, the final answer that is exact, I believe, is 10.6 repeating. So even with just 4 rectangles, notice that Simpsons Rule actually works out quite nicely. So let's erase some of this. Okay, and so notice that this is, let me make sure we understand that these are both, what I'm calling for Simpsons for is 2 times 4 midpoint and trapezoid 4 divided by 3. Again, most books would call this Simpsons 8. So it turns out that Simpsons Rule is equivalent to approximating the curve with a quadratic function on each piece, that is a little parabola graph, so that on each piece the parabola hits at both ends and the middle of the interval. So if we take one of these intervals again and we take this point here at this end, this point at this end, and the point right here in the middle, we make a parabola that hits all 3 of those points, and it turns out that Simpsons Rule works out to be that. I won't prove that just right now. We need to do some other things first, so we may come back to this in a later video and prove that statement there. So let's see if we can put all this stuff to work for us. So here's the table, and let's assume that this function is integrable, that the limit that defines the integral does exist, and we have a set of data here. Notice there are actually 7 data points, but I want to do it intervals of width 2. So 0 to 2 is going to be one interval. So there's one interval. From 2 to 4 is a second interval. And from 4 to 6 is a third interval. So that means you're going to have 3 intervals. So notice that 2 is delta x. Delta x is b minus a over n. That's 6 minus 0 over n. So n is, saw that for n. We see n is 3, and we already have seen that. So we're going to divide this up into 3 intervals. Notice then on the interval, I have information about what's happening at the left, right, and middle of that midpoint of that interval. So I have enough information to do Simpsons Rule. So what I'm going to ask you to do at this point is stop the video, take the data in this table, and come up with what I'm going to call Simpsons 3, but also come up with left 3, right 3, trapezoid 3, midpoint 3, and Simpsons 3. So left, right, midpoint, trapezoid, and Simpsons estimates for this particular function based on the data in this table. Okay? Once you've done that, then come back and check your answers as we proceed. Press pause now. Well, let's take a look here. So, if we want to do right Riemann sums, we start with the first interval here. We go to the right end of the interval and take its height, which is 14. Now, the delta x is 2. So but it's going to be 2 every time. So all these should be multiplied by 2. I'm going to factor that out front. Since we're using common widths, you can always factor out the common width, the delta x. Now for the next interval, which goes from 2 to 4, we go to the right side of the interval, which is 4. Find the y value that goes with that, f of that right side, f of 4, and that's 18. That's what you put here as y values. And then the last interval here, we go to the right side of the interval, find the height there. So what we're doing is each time these things in the parentheses are the y values. So you're just summing up 3 y values, 3 f values, f of x, at the right hand of the interval. So there's the interval. When I say right, I mean I want my table lined up so that these x values or input values go left to right on the number line, smaller to larger. So looking at the one interval, we put a y value. Which y? The one all the way to the right, 14. Then we look at our next interval. Put a y value. Which one? The one all the way to the right, 18. Then we go from 4 to 6. Go to which one? The one all the way to the right, 13. Add those y values, multiply by the common width of 2, delta x, and we got 90. How do we do left Riemann sum? Well, again, we take each interval and we plug in a y value. We figure a y value. Multiply by delta x. Since the delta x is constant, we're going to factor it out. So we're really just adding up all the heights of each interval and then multiplying by that common width. Okay, so which one of these heights do we choose? The heights of the y values. Well, we choose the one at the left end, which is 12. Then for the next interval, which goes from 2 to 4, we go to the left end, which is 14 for the height. And the last interval includes these 3 points. We go to the left part of that, the left end, and that's 18. And we add that up as 44, and we multiply by the common width, which was 2 every time. 0 to 2 is 2, 2 to 4 is 2, 2 to 6 is 2. And that gives us an estimate of 88. Now to get the trapezoid estimate, all we do is take left plus right and divide by 2. So halfway between 88 and 90, of course, is 89. Now how do we do the midpoint rule? Well, we do it just like we did the left and right, but this time when we choose the height, for example here, we're going to choose the height for the one in the middle. So we're going to choose 13, 16, and 17 for those heights. So we're going to replace these numbers here in the left and right by those heights, 13, 16, and 17. Add those up, multiply by 2, it's 92 for the midpoint rule. Now of these numbers here, 88 and 90 are about equally accurate probably in general. We want to average those to get the trapezoid. So trapezoid should be better than right or left. Midpoint should be a little better than trapezoid. So the best estimate we can come up with is Simpsons Rule estimate, which takes 2 times the midpoint plus 1 trapezoid and divide by 3. So that's 2 times 92 plus 89 and then divide by 3. Don't forget your parentheses around the numerator there if you do it on a calculator. And that turns out to be 91. So which one of these is the best estimate? Simpsons Rule is our best estimate. So 91 is going to be very close to the area for just about any function we could come up with that goes through those points in that table. Okay, I'll come back and do a little bit more work with this idea and how we can use technology to help us find some shortcuts to this process.